What is up, everyone? It's Mr. Holtz, and today we're going to be talking about units and unit conversions. So I'm going to be showing you the slides that I've added to our Google Classroom. Again, these are just going over the different units that we're going to be using, talk about some different variables that are important in chemistry that we will be running into for the rest of the year. And then we'll talk a little bit about how to convert units. How do we use dimensional analysis to go back and forth between things like milliliters and liters, or grams to kilograms and stuff like that, all right? Or if you have units that are in the standard system and you need to switch them over to the metric system, again, what does that dimensional analysis look like? And how do we go through those unit conversions? So let's take a look at blowing through some of these slides. All right, the first thing that we're going to be talking about is, what is a variable? Well, the definition of a variable is right here. It's an item, factor, or condition that can be controlled or changed, okay? Now, something that we are going to control or change is different than something that is changed just automatically. So let's go over what these two examples are. And hopefully, let's see if I can move this guy. All right. So an independent variable is the variable that is changed or controlled in a scientific experiment to test the effects of it on something else, okay? So the independent variable when you are running an experiment is whatever you are changing to see how that change causes some effect, all right? Whereas the dependent variable is the variable being tested and measured in a scientific experiment. So this is the outcome, what changes based on the change that you made previously. So let's take a look at some examples here. Oh, let me scroll up. Okay, so let's say you're testing how effectively plants grow in the sunlight versus in a cloudy area, right, where there's not very much sun, somewhere like the Pacific Northwest. So the amount of sunlight is something you are changing, right? You're either putting this plant in a high sunlight area or in an area where there's no sunlight at all. So the amount of sunlight that this plant gets, because that is the factor you specifically are changing, that would be our independent variable, right? Something that you control. The dependent variable is what changes in response to that. So you are not the one controlling whether the plant grows up straight looking at the sun or whether it wilts and grows poorly, right? That growth of the plant is dependent on the sunlight. So the plant growth, if that's what you're measuring, right, the amount of plant growth would be our dependent variable here, okay? So the independent variable is what you control, and the dependent variable is what you study based on the change in what it is that you're controlling. All right, let's move on. So here's just a list of different variables we're going to be using this year. You can look at them right now. We'll talk about each of them once we get to each unit. So right now, we're only going to be learning about a few of them, because specific heat capacity, that's like unit 6, right? That's thermochem. pH and pOH, that has to do with acids and bases. We'll get to that in unit 8. So a lot of these we might not cover yet, but just know that there are a bunch of them out there, and we'll be learning a lot of different variables this year. Okay. So again, we're going to learn a lot of different stuff. Plenty of these variables go into equations, as you can see here. So this is a couple of these variables in action. We'll have to do with concentration, volume, moles, let's see, heat or energy. So depending on what we're doing, lots of different variables in play here. So let's take a look at some of the more common ones that we should know off the bat, to come at the beginning of the year knowing a good amount of background, all right? So the first thing we're going to talk about is mass. Hopefully you have a good idea of what mass is. It's similar to weight. Once you get into physics, there are some technicalities as to why they're different. Weight more has to do with the effect of gravity on mass, whereas mass is a standard amount. So mass is the amount of a substance, right? How much stuff is in something. So as an example, let's look at this piece of paper and this rock right here, right? Obviously, a piece of paper is not very heavy, right? Everybody's held a piece of paper. Everybody's held a rock. Generally, a rock, especially if that rock is the size of a piece of paper, right? An 8.5 by 11 sheet of paper, that rock's probably going to be pretty heavy. That's because there's a lot more stuff in this rock than there is in this paper, right? So the rock has more mass because there's more stuff in that thing. So mass, we usually just put something on a scale and measure how much mass it is based on its weight, right? How much it presses down on a spring. So we'll deal with this later on, but mass is pretty straightforward. The way that we measure mass in chemistry is with the gram. So generally in society, right, in American culture, when we ask like, oh, how much do you weigh? Your response is in pounds, but pounds doesn't help us because that's not an easily convertible unit. And I'll talk more about the metric system once we get through these first couple examples. But the way that we measure, or the unit that we use when we're talking about mass, is grams. Okay, so a cup of water weighs 100 grams or something like that, right? We don't use ounces, we don't use pounds, we use grams. So if you need to convert it, here are the conversions down here. So 1 pound, or 1 pounds, should probably say 1 pound. 1 pound equals 0.454 kilograms. And we'll talk about how to convert from grams to kilograms once we get to the metric system. But this is our relationship here. Okay, if you wanted to do the other way around, 1 kilogram is the same as 2.20 pounds. Okay, now again, they represent the same amount of stuff. There's the same amount of a substance in 2.2 pounds as there is in 1 kilogram. But again, the pounds are using the American system, and the kilogram is from the metric system, which is what we use in science. And that has to do with the ease of converting between one unit and another in the metric system, which we'll take a look at. All right. So mass is how much of something do we have? Length. Okay. Length is pretty straightforward. Just like, again, I would ask you guys, how tall are you? But we don't use feet and inches. We actually use meters and centimeters, or other meter-based units. So what is length? Hopefully it's pretty straightforward. Length is the measurement of something from one end to the other. So if you're measuring how tall you are, you're measuring the length from the bottom of your feet to the top of your head, right? Like I said, our base unit for length is the meter. So a meter is about a little more than a yard. Okay, so in America we use inches, and you need to know that 12 inches is the same as a foot, because if there's no easy conversion if you don't have that factor memorized, right? Same thing with feet and yards. If you need to measure yards, you have to know that 3 feet is equal to a yard, or you won't be able to do this conversion or use these measurements interchangeably. Similarly, we use miles. So if you're ever watching TV and you hear British people talking about driving kilometers per hour, right? They use kilometers because kilometers is based on the meter metric system. Whereas if you're talking about miles in America, if you don't know that a mile is the same as 5,280 feet, there's no way you're going to be able to do that comparison between feet and miles, because that's a factor that you have to memorize. The metric system, you don't have to memorize as much, because it's really just moving decimal places. So it would be like if 1.2 inches was the same as 1.2 feet, or if 12 inches was the same as 1.2 feet. But that's not the case, right? You have to know all of these, you have to memorize all these conversions for our system in America to make sense to you. So here are the conversions down here if you want them. 1 inch is the same as 2.54 centimeters, and 1 foot is the same as just a little less than a third of a meter. Okay, so 0.305 meters. But again, length is really just how long is something, or what is the distance from some point to another point. Okay. Volume. So volume measures how much space something takes up. Now, a good way to think about this is if you're packing things to go somewhere, go on a road trip or move, right? You're packing stuff into a box. So if I had like this water steamer, or this water heater for tea, okay? Doesn't matter if there's water in this or not, it's gonna take up the same amount of space in the box that I'm packing this in, regardless of what's in here, right? That space is already taken up by this glass casing, okay? So volume is how much space something takes up. Doesn't matter if the space is full or not, it's taking up that space anyways, all right? Ooh, almost broke a graduated cylinder. That would have been bad. Okay, give me just a second. I'm gonna pause it and go take care of the cat. All right, moving on. Okay, so volume is how much space something takes up. So keep in mind, space is 3-dimensional, right? It has the X direction, the Y direction, and the Z direction. So when we're measuring out volume, especially volume of something like a cube, we need to take that into account. And I'll talk about that once we get to using different kinds of units to measure volume. But what you should know is that our base unit to measure volume is the liter, okay? Now a liter, if you've ever had a Nalgene, one of those like really thick plastic water bottles, they're about this big, ish, right? That's about a liter, okay? So 1 liter is about the size of a Nalgene. If you have a hydro flask, one of those tall, skinny hydro flasks, that is about 3/4 or 750 milliliters, which is about 3/4 of a liter, okay? All right. So the last unit I want to talk about before we move on to talking about the metric system and how to use the metric system for conversions is moles. Now, a mole is a concept that has to do with an amount of a substance, but it means amount in terms of the number of things, okay? Not amount in terms of like, I need 5 grams of table salt or 5 grams of sugar, right? 5 grams is still an amount, but that amount is based on a mass, okay? So the way that we measure out a mole is based on a specific number. Now that number of a mole is this, okay? So N is the variable we use to represent moles, but 1 mole is equal to 6.022 times 10 to the 23rd something. Okay, now this something could be atoms. If you're talking about individual atoms like neon gas or helium gas, right? Those don't form compounds because they're noble gases. So we're really only going to be measuring them off of individual atoms. Could be ions, if you're talking about individual ions, or it could be molecules. Molecules. All right, I'm still getting used to this writing pad. So a water molecule, right? A water molecule doesn't just have one atom in it. Water molecules have the formula H2O, meaning there are 2 hydrogens, right? And 1 oxygen. So this is all in 1 water molecule, which means 1 mole of water has 6.022 times 10 to the 23rd total molecules of water, okay? Now something like glucose. So glucose is a large molecule, right? And glucose has a big ring of carbons and oxygens and hydrogens, so it's much bigger than a water molecule. However, 1 mole of glucose is still 6.022 times 10 to the 23rd molecules, okay? Now, that total amount of molecules ends up weighing more. It has more mass because the molecule of glucose is way bigger than the water molecule, just because of the number of things that are in that, right? So it's kind of like comparing a dozen eggs to a dozen elephants, right? Clearly, the eggs are going to be way, way smaller. They're not going to weigh nearly as much. But the fact that they're smaller is not what we're concerned about, right? We're concerned that we have the same number of them. So scientists don't care about molecules that are bigger or smaller, or ions that are big or small, or atoms that are even by themselves, right? It doesn't matter. What matters is that we have this amount of them, okay? And we have come to a standardization to give us an idea of how do we figure out how much 6.022 times 10 to the 23rd molecules of anything is, right? We can't measure out individual molecules. And even if you did, by the time you were done, you would die before you were done counting these. A human life is literally not long enough for you to count out this many molecules individually, even if you started from the minute you were born. So we have come to a standardization, which is based on the periodic table. So if you come to the periodic table, let me open up a new tab for the periodic table. What you'll find is that when we look at these boxes on the periodic table, the number at the bottom refers to the atomic mass, right? We talked about the atomic mass. It's comprised of the average amount of neutrons and protons in the nucleus, okay? So because the average atomic mass of hydrogen is about 1, right? It's a little, just barely over 1, but that decimal place is pretty far away. So hydrogen has kind of become our standard for atomic masses. So what we refer to as atomic mass is the atomic mass is equal to atomic mass equals 1 mole of that thing. Okay, so the atomic mass of hydrogen, or the atomic mass of hydrogen is the mass of that many molecules of hydrogen. Now, there is the slight difference here that when we talk about hydrogen, we never actually find hydrogen. If you think of this as one hydrogen atom, in nature, we never find one hydrogen atom by itself. You might have heard of hydrogen gas, or if you've ever heard of the Hindenburg explosion I think it was in the 40s in Germany, or in the mid 20th century. So hydrogen gas was actually holding up the Hindenburg because just like in a helium balloon, right? Helium is less dense than air. So if you let go of the balloon, it's going to float away. Hydrogen gas is also less dense than air. So at the time, hydrogen gas was easier to make and cheaper than helium gas. So hydrogen gas is what was used, and hydrogen gas has the formula H2. So because there are two atoms of hydrogen in that molecule, the atomic mass is actually two hydrogen atoms put together. So usually we round hydrogen to 1.01. So this would be 1.01 plus, make sure that decimal point is there, 1.01, which obviously is 2.02. So this many grams would equal 1 mole, or 1 mole of hydrogen, okay? This is the atomic mass, or the molar mass, because this is the mass of 1 mole of hydrogen gas. Now, the only way we needed to figure that out was that in hydrogen gas, there are two atoms of hydrogen, right? Here's one, here's another one. So the molar mass is the mass of 1 mole, which is really just adding up the atomic masses of everything that's in there. So let's see if I can scroll down here. All right. So again, for example, water looks like this, right? An oxygen atom with a hydrogen atom on each side. And we'll talk about the structure of atoms later. But if this is a water molecule, and I wanted to figure out the mass of a mole of water, or the molar mass of water, I would have to take the hydrogen mass plus the oxygen mass plus the hydrogen mass of the extra hydrogen, right? There's two of them. So because the hydrogen mass, like we talked about, is 1.01, I know there's two of them here. So 1.01 plus 1.01 plus, and generally oxygen, you'll find it as 15.999, right? We usually round that to 16 because it's pretty close. So plus 16. So the mass of all of these put together is 18.02. And again, if we wanted to make it a mass, because we're talking about molar mass here, we need to use our mass unit, which we know our base unit for mass is grams. So 18.02 grams equals 1 mole of H2O. Okay, so this is the molar mass of water. So if you were going to measure out 1 mole of water, you'd measure out 18.02 grams. And you could do that on a scale, just dropper at a time. So this is how you find the molar mass of a substance. But again, keep in mind, a mole is based on the number of molecules we have, right? So here is the important number, 6.022 times 10 to the 23rd, okay? So because a water molecule is bigger than a hydrogen gas molecule, right? Up here is our hydrogen gas, two atoms of hydrogen in that one molecule. That's pretty small. It has a really small molar mass. Whereas water is obviously much bigger, and because it has something else in it, right? It has that oxygen atom. So because the oxygen atom is here, and this molecule is so much bigger, so much heavier, the molar mass of 1 mole of water is going to be way more than the molar mass of hydrogen gas. All right. So here we have the description of a mole, right? A mole is a number that is used to describe the amount of atoms, molecules, and other particles. But again, it's based on whatever that substance is made up of. So for water, the mole is based on the fact that the water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. Now, if you actually wanted to measure this out, just as an example, 18.02 grams of water is about the same as 18 milliliters. So the 18 grams of water, this is about 18 grams of water. As you can see, it's not very much, but water is not a huge molecule in chemistry, so that's all right. But that is what it would look like in terms of measuring it out. So here are some other examples, all right? Here is a mole of copper atoms, okay? So here's copper. Now it's just copper, so the only thing in here is copper. Now, because copper has an atomic mass of 63.546, this would be 63.5 grams of copper. Now it's just copper, there's nothing else in here, so that we don't have to add anything else, and it's not a compound, it's just atoms. So 63 grams of copper is what this is. This is a mole of copper. Now again, it might not look like a lot, but when we get to much, much bigger molecules like sucrose, okay, sucrose is a big sugar molecule. It has 2 rings made out of lots of carbon, hydrogen, and oxygen atoms. So it's got a bunch of carbon with an atomic mass of 12, a bunch of oxygen with an atomic mass of 16, and a bunch of hydrogen with an atomic mass of 1. Now, when you add all of those up, the overall molar mass of sucrose is actually 342 grams. Okay, that's a ton. But think about how many molecules you would need, or how many atoms you would need within that molecule to make that up. Still quite a few, but when you start putting them together in the molecular structure, it makes a little bit more sense. So once we'll get to that later this year, and what does it look like to draw molecules and stuff like that. But this is 1 mole of sucrose, okay? There's clearly a lot of sugar in here because there's a lot of stuff in 1 mole of sucrose. Again, if this is our dozen eggs, it's not a lot, but it's still a dozen. It's a dozen, and that's the only thing we care about, right? This is a mole because of how many molecules are in here, okay? Doesn't matter that the molecules are smaller than they are in sucrose. That's why there's so much more stuff in here, right? A dozen elephants weighs way more than a dozen eggs. But again, that's a property of the thing that we're measuring, not how much of that thing we're measuring. So hopefully that makes sense, okay? So in the concept of a mole, we are concerned with, do we have 6.022 times 10 to the 23rd atoms or molecules or whatever, right? Doesn't matter what the size of those individual molecules is, because we want to know whether or not we have that number of them, okay? We'll talk about moles more as we move throughout the year. So let's talk about the metric system, okay? The reason we use the metric system, like I mentioned earlier, for grams, meters, and liters, right? Those are our base units. The reason we use the metric system is because it's super easy to convert back and forth. So, for example, let's say that I have, if I measured this out, right? This is 342 grams. So 342 grams is the mass of this Erlenmeyer flask, okay? Now, if somebody asked you, oh, how many kilograms is 1 mole of sucrose? Okay, clearly this is not in the units of kilograms, it's in the unit of grams. So the reason we use the metric system is because it's super easy to convert back and forth between any of these prefixes. Now the prefix tells us how it relates to the base unit, okay? So it's not in here, but the base unit, these grams, meters, and liters, would be this middle dividing line down here, okay? Now, as we go above this line, we move to deca, hecto, kilo, all these other prefixes. You can see that the multiplication factors are large numbers, right? 10, 100, 1,000. So as we go below, when we use the prefixes that are below the base unit, deci, centi, milli, micro, right? A microsecond, a nanosecond is way shorter than a second. So a decigram, a centigram, all of these numbers are smaller than 1, which means these are a fraction of the base unit, okay? So a decimeter is a tenth or 0.1 of a meter, right? 10% of a meter. Whereas a decameter is 10 meters, okay? 10 is the multiplication factor for that prefix. So again, let's convert this value of 342 grams to kilograms. Now, you guys will learn the prefixes as we move along. The prefixes are here if you want them, okay? So K is our prefix for kilo, right? Kilo is our prefix right here. And again, we're still using grams, so you have to keep the G unit in, or else we won't know what we're actually measuring. But notice here, a kilo of whatever we're talking about is 1,000 of the base unit, okay? Which means 1 kilogram equals 1,000, oh, that's not 1,000, 1,000 grams, okay? These are the same thing. That's why this says 1,000 right here, okay? It also has it listed in scientific notation if you want the 10 to the exponent, all right? So how do we convert from our starting value to something else using this conversion factor? Well, the easy way to do it is I always do it like this, okay? Draw a line, draw a multiplication symbol, draw another line, and then your equal sign. These lines are not going to be big enough for me, but what we got, okay? Equal sign. Okay, so we're starting with 342 grams. That is our mass, okay? Now, whatever you're starting with should always be your first value, right? Because you're starting from there and you're going somewhere else. So you want to start with whatever value you have. Now, the place we would start is right here, 342 grams. You got to make sure you have the unit or you might not cancel things out correctly. Now, if we want some answer in terms of kilograms, okay, here's going to be our answer, and we need it in units of kilograms. So somehow, right, we need to get rid of this gram unit because we don't want it in our final answer. That's where this conversion comes in, okay? If we know that 1 kilogram and 1,000 grams are the same thing, let's put 1,000 grams on the bottom, because once we multiply and divide, we want these units to cancel out. So the second thing you should do is, once you find your conversion factor, place the value with the unit you're getting rid of on the bottom of the next fraction. Okay, that will force this gram unit and this gram unit to cancel out. Now, because just like in algebra, we can only subtract 2 if we're subtracting 2 from both sides, right? If you and your little sibling are given equal, like if your parents give you and your little sibling 5 cookies each and then realizes that your cousin didn't get any cookies, it's fair if you both get 2 taken from you, right? Because then both you and your little sibling still end up with 3 cookies. So as long as we can keep things equal, we can only make a change to one side if we make the change to the other side. So we can't make this value when it ends up as something else. It still has to equal 342 grams, or else we won't be representing that value correctly. So we can put 1 kilogram on the top, because again, 1 kilogram and 1,000 grams are the same thing. And anytime you take something and divide it by itself, it's 1, right? So we're really just multiplying this value right here by 1 and changing its units. So we're representing it as something else, okay? So it's still the same amount. We're not changing the amount of stuff we have. We're representing the same amount of mass, but we're using a different unit to do so, okay? So again, here's a gram on the top, here's a gram on the bottom. Those units are going to cancel out. 342 times 1 is still 342. But as soon as you divide it by 1,000, we move the decimal place over 3, right? 1, 2, 3. So we end up with 0.342 kilograms. So that is our answer for converting 342 grams into kilograms, okay? Let's go through one more example. If I have some distance that measures 22.4 meters, and I want to know how many centimeters that is, how do we convert from meters to centimeters? Well, let's take a look at our metric chart, okay? So again, we're starting with meters, okay? That's our base unit, and we want to go to centimeters, all right? So if we go over to our chart, our base unit is this line in the center, right? That's where our meters would be. Now, if we're switching or converting to centimeters, here's our conversion prefix, right? Our C. Now, again, the M that comes after the C refers to the meters, not milli, because we can't have 2 prefixes for something. That doesn't make any sense. So the prefix centi means 0.01 or 1/100th of something. So if 1/100th of a meter is the same as a centimeter, that means that 100 centimeters is the same thing as 1 meter, okay? So 1 meter equals 100 centimeters. Now, if you want to use the decimals, you can. I prefer not to, but it would be the same as saying 0.01 meters equals 1 centimeter, right? So if you move these decimal places over 2 for both of them, right, we'd still have the same equivalence. I like to use whole numbers, but if you want to use the decimal points, you can. Go for it. I'm going to set this up the same way, okay? My long first line, long second line, and then we have our equal sign over here. Okay, so again, start with whatever value you're starting with, or whatever in this problem, we're starting with 22.4 meters. Okay, that's where we're going from to what we are heading to. So, whoops, not centimeters yet. We're getting there. 22.4 meters. Okay, now again, because we don't want meters in our final answer, you should always use this conversion, whichever one of these you're going to use, and put the unit you started with on the bottom of the second fraction so that we can make sure we cancel it out, because we don't want it in the end, right? We want an answer that comes out in units of centimeters, okay? So I'm gonna put my 1 meter on the bottom down here so that my meter units will cancel out, because I have one on the top, one on the bottom. And then I know, because of the conversions I wrote down, 1 meter is equal to 100 centimeters. All right, so we've got our conversion. Our units are going to cancel out. We're left with just centimeters. So 22.4 times 100, move the decimal place over 1, 2, and then you divide it by 1, which is the same thing. So we end up getting 2,240 centimeters is equal to 22.4 meters. Okay. Hopefully this has given you guys a good idea of how to do these basic unit conversions. It'll get more complicated once we get to unit 3 and we talk about stoichiometry, but don't worry about that yet. All right. So that is why we use the metric system, because like I said earlier, we're going to use not only a ton of variables in chemistry, but we also use a bunch of different equations. Now, depending on the equations you use, some of these might require specific units, right? So if we're using a volume in this equation, you might have to use liters instead of milliliters. Now, if you're measuring something out, right, this is measuring milliliters, but if I need that unit in liters to plug it into the equation, I have to be able to go through these kind of unit conversions, or I won't be able to do the actual calculation, right? I'll never come up with an answer. So the reason we use the metric system in science is because it's super easy, because all you have to do in converting in the metric system is move the decimal place one direction or another, all right? So moving on to the last few slides, density, okay? What is density? Density is the ratio of the mass of an object to its volume. Now, hopefully you guys know the formula. Density equals mass over volume. So it's really how much stuff do you have in a given space, right? And space is 3-dimensional. So if we look at these two cubes here that are drawn, obviously this cube on the right has much more stuff in it, even though these cubes are the same size. So because this has more stuff, right, more substance, it has more mass, it has a greater mass to volume ratio, meaning this number is bigger than it would be in this cube because there's much less stuff. You can see that by the circles. So this box has a much greater or heavier, not heavier, much greater density because there's more stuff in the same amount of space than there is in this block. All right. Now, the base units that we use for density are grams per milliliter. Sometimes you'll see kilograms per liter, which really means the same thing, but we'll cross that bridge when we get there, all right? But most of the time you use grams per milliliter, okay? And this picture right here is just representing that this substance down here that looks kind of dark, maybe brownish, compared to the green substance, compared to the blue and red and yellow, right? The reason we have these colorations is because the different liquids in these layers have high densities at the bottom and slightly lower densities as we move up and up and up, all right? That's why oil floats on water, because oil has a much lower density than water does. All right, so molarity. Molarity has to do with concentration. Now, what is a concentration? A concentration is a ratio of solute, or the substance that's being dissolved, to solvent, or what is dissolving the stuff. So let's take a look at this picture down here. So notice here, we can dissolve salt in water, and you guys all know this, right? Salt dissolves in water. That's how we have the ocean. If you've ever had to gargle with salt water, that's how we make it. So The solute is the dissolved particles in the solution, right? So salt dissolves in water, but it's still there, right? Even if you can't see it once it's dissolved, that doesn't mean it's disappeared. But the salt would be, in this case, the solute, or the stuff that is being dissolved, okay? The solvent is whatever liquid we're using to dissolve that stuff. In this case, our solvent is water, because the water is what is dissolving the salt. So obviously, we can make things that have a high concentration and a low concentration. So instead of talking about salt, you guys could imagine making like lemonade, right? So if this was lemonade powder, you could add 1 scoop to the water. You could add 12 scoops to the water. Now, you probably wouldn't want to drink it after 12 scoops. Why? Because it's really concentrated, because you have more stuff in the same amount of liquid, okay? So the ratio of solute, the stuff we're dissolving, to solvent is how much stuff did we dissolve, and how much total stuff did we dissolve in, okay? So dissolving 12 scoops of lemonade powder is going to give you a higher ratio of solute to solvent, which means 12 scoops is way more concentrated than 1 scoop, all right? Now, generally, the way that we measure molarity, which is the unit that we use to determine concentration, and we use it with this capital M. We'll talk more about this once we get to unit 3, but molarity is how many moles of our solute, so again, coming back to moles, how many moles of our solute do we have per liter of solution? So notice here, we have to use liters. It is volume, but it's based on the unit of liters. So you can't use milliliters, you can't use deciliters. So this is a good place where knowing how to use those volume metric conversions comes in handy. All right, moving on to pressure. So pressure, as it says here, is a force exerted by the substance per unit area. So a lot of times we use pressure in America, like pounds per square inch. So pounds is a force, right? Pounds is a force on an area, and square inches is an actual area, right? Inches by inches is a square, okay? That's how we calculate an area. But pressure is the force exerted on that. Now, again, we'll talk more about this once we get to gas, but just notice that more molecules in a smaller space creates a greater amount of pressure on this piston than it does when there's lots of space, right? Imagine having a sandwich bag full of air and just leaving it on the counter versus what happens when you push your hand down on the plastic bag, right? Imagine it's sealed. So you're pushing your hand down on this sandwich bag that's just full of air. Eventually, you'll create so much pressure that it'll pop, right? Because you're trying to force this amount of stuff into a smaller amount of space, which creates a greater amount of pressure. But again, we'll talk more about this as we move on and get to some later units this year. Okay, the next thing we should talk about is temperature. Now, hopefully you have a general idea of what temperature is, right? It's the degree or intensity of heat. It's how we measure how hot or cold something is. And this is going to become really important once we start talking about gases. Temperature of an object reflects the internal amount of kinetic energy, okay? So these lines here represent, these smaller lines represent these molecules moving slower, and these bigger lines represent these molecules moving faster, right? High movement versus low movement. So high movement means high temperature, okay? Boiling water, those water molecules are moving really fast when water's boiling. That's going to be way hotter than water at room temperature, okay? The molecules are moving much slower. So just keep this concept in mind, but we'll come back to this. Now, in America, we measure temperature in degrees Fahrenheit, right? Like, oh, it's 86 degrees Fahrenheit out right now. Now, in science, we don't use Fahrenheit because the scale is not very helpful to us. If you didn't already know, water boils at 100 degrees Celsius, and it melts at, it melts at 0 degrees Celsius. So the 0 and the 100 numbers make the Celsius scale super helpful in chemistry, or just in science in general. Whereas knowing that water freezes at 34 degrees Celsius or 34 degrees Fahrenheit and it boils at 212 degrees Fahrenheit is not very helpful because those numbers aren't as easy to use. So we'll get to some conversions in just a second. Another scale that we use to measure temperature is the Kelvin scale. Now, this is going to become important again once we start talking about gases. But one thing I really want to mention here, notice this says metric unit, degrees Celsius and Kelvin. It does not say degrees Kelvin. If you are asked the temperature of something by another scientist and you say, oh, it's 300 degrees Kelvin, you will be laughed at, okay? We don't use the term degrees on the Kelvin scale. We'll talk about more as we move throughout the year, but if you've heard the term absolute zero, right? Absolute zero is where molecules are not moving at all. That is 0 Kelvin. It's not 0 degrees Kelvin, it's just 0 Kelvin, okay? So the Kelvin scale is based on that absolute zero quantity, which is why we don't use degrees. If you need them, here are the conversions between Celsius, Fahrenheit, and Kelvin. But again, we'll talk more about that once we start using it. Okay, energy. What is energy? Well, energy in terms of science, energy is defined as the capacity for doing work, right? Can you do work? Can you make something that runs on electricity run? Is there enough electrical power, right? Pushing the pedals to run a bike. Okay, you're doing work. You're moving your body from one place to another. Light is a type of energy. Heat is a type of energy. Chemical energy is stored in bonds, and we'll talk about that all year. So there's a lot of different kinds of energy or forms that energy comes in, but they're all generally defined as the capacity for doing work. Now, the type of energy will reflect what kind of work is being done, but again, we'll talk about that later this year. Now, the base unit for energy in science is joules, and not joules like J-U-U-L, that doesn't make any sense, J-O-U-L-E-S. So this is our base unit for energy, and again, we'll talk more about that once we get there. pH is referred to as potential hydrogen. I don't really want to talk about this now because this isn't a concept we need until like unit 8. So we'll get to this when we talk about acids and bases. Qualitative versus quantitative. All right, so in general, we have two different ways of describing quantities or variables in chemistry, okay? Now, quantitative or a quantity has to do with numbers, okay? 1 fish, 2 fish. 1 fish is a quantity, 2 fish is a quantity. A qualitative description has to do with the qualities or characteristics, right? Doesn't have anything to do with the numbers. A fish that's red, the fact that it's red is a quality of that fish. A fact that this fish is blue is a quality or a characteristic of that fish, okay? So these are the two kinds of measurements or pieces of data that you can pull from doing experiments, right? Either having to do with numbers or having to do with qualities. Accuracy versus precision. So this is a pretty, this concept can be hard to remember, but this is a great diagram to help us keep in mind what the difference between those two things are. So accuracy is how close measured values are to an accepted value. So in this case, the accepted value or our goal is the bullseye, right? So low accuracy is you're missing the bullseye, okay? Low accuracy, missing the bullseye, right? This one's pretty close, but most of them are pretty far away. Most of these are pretty close to the bullseye, right? High accuracy. And these are all super close to the bullseye, or if not right on them, okay? High accuracy. They are meeting the goal or not meeting the goal, all right? Whereas precision is based on how close your measured values are to each other. So in science, we should always take multiple measurements, right? One measurement is not good enough because you need to be able to find an average that represents the values that you tested, okay? So the precision is how close are all of your values to the other values, right? None of these values are close to each other. This is very, very low precision. Now, these are a little bit closer, but they're still not great. So this is better precision, but it's still not great. Notice how these dots are all super close to each other, and these dots are also all super close to each other. So both this top example and this bottom example have super high precision because all of the quantities or all of these data points are super, super close to each other, regardless of how close they are to the goal, right? Because that has to do with accuracy. So keep these two definitions in mind. All right, significant figures. So significant figures is kind of a complicated concept that trips people up a lot, but basically, all digits of a measured quantity, including the uncertain one, are called significant figures. Significant figures are important in science as they imply a certain level of precision, right? How close things are to each other, in terms of measured values that is associated with a given number. So in this thermometer right here, you might be asked, oh, what's the temperature on the thermometer? Okay. Now, if you didn't have this zoomed in section, you'd say, well, it's about 30 degrees. Okay. Because you can see that it's pretty close to this 30-degree mark. It's above 20 and it's below 40. But that would be a guess, right? We don't have finer tuned measurements. There's not more lines within these. So the fact that you're guessing by zooming in here and saying, well, it's a little bit less than halfway between 25 and 30. So let's just say 27, okay? The 7 is an estimated digit. It's uncertain. You don't know it. And that has to do with significant figures, okay? Significant figures tells somebody how accurate and how precise you are in terms of knowing those values, all right? So we don't know this 7. The 7 is a guess, but if there were other distinct lines for measurements here, we could come a lot closer to getting a much more accurate guess, okay? So significant figures, there's some general rules, but here are the general rules for significant figures. And this video down here will also be very helpful. So significant figures, basically, whenever there's a 0 in a number, it does not always mean it's significant. Let's see. So these are just the rules for zeros. Now, the reason there's only rules for zeros is because whenever there's a non-zero number, right? Non-zero numbers like 1, 2, 3, anything from 1 to 9, those are always counted as significant digits. And this guy down here, Tyler DeWitt, does a great job at explaining this. Okay, I highly recommend you watch the video. I'll talk more about the rules on how to use them later on. So don't worry about this now, but just take a look at these. I might write them in your notes because it would be good to have so that you can look back on. But just know non-zero numbers, anything from 1 to 9, always a significant number. So you're always going to count it. Now, what do I mean by you're always going to count it? Well, when we talk about significant figures, it's basically looking at a number and determining whether all of the values in that number are significant. So here are a couple numbers, right? 40, 41, 412, 4013, or 4113, 41.13, 41.130. So these are a bunch of different numbers, and depending on how you look at these numbers and depending on what's in them, they have different amounts of significant figures. So basically, you would determine, is this significant? Is this significant? Is this significant? Is this significant? Okay, so all the 4s, all the 1s, all the 2s, all the 3s, anything that's not a 0 is always significant. So all of these numbers are always going to be significant, okay? Now, however, this number is not significant. We'll come back to why in a minute. Let's go back here. All right, so zeros between non-zero digits are always significant. 1005 has 4 significant figures because these zeros are in between non-zero numbers. They're important, okay? We keep them there. Zeros at the beginning of a number are never significant, okay? Never significant. They merely indicate the position of the decimal point. So the fact that there's a 0 here and there's a 0 here do not count towards the significant figures, okay? Just like this one only has 2 significant figures. None of these zeros are important because if you are measuring something that's 0.0026 centimeters long, skipping over the number here and the number here are important to get to the number you can actually measure, right? But the fact that these 2 zeros exist don't have anything to do with implying how accurate or how precise your measurement is, okay? Only the 2 numbers actually give us any information about what you're measuring. So those are the only 2 significant digits in this whole number, all right? However, zeros at the end of a number are significant, all right? If the number contains a decimal point. So, for example, their example was like 0.0 or 0.200 versus 200, okay? If these are both grams, the measurement of 0.200 grams means you measured this 0 here. Either your scale goes to that number and you were able to get a measurement for that, or you're able to calculate it, okay? Same thing here. The difference would be if you had a measurement that was 0.20, okay? If you were measuring something on a scale and you got to this 0, but that's the last digit the scale gives you, this is a significant figure because you know that it's a 0, right? This is a measured value. You're getting closer and closer to smaller decimal points, meaning your measurement values are getting more and more and more accurate the further your decimal places go, okay? Knowing that this 0, this extra 0 is here makes this number a more accurate measurement than this number, okay? Because we have that extra decimal place. If you know this is a 0, we don't know what this number is, right? There's no number here because we can't measure it. And because you can't measure it, you don't know how accurate your measurement is. Here, we know how accurate this measurement is because we have a value here. So zeros at the end of these numbers after the decimal are significant. Now, the difference is zeros at the end of a number that does not have a decimal are not significant. And the reason is that this is assumed that this is a rounded number, right? If you had 200.02 pieces of paper, and I need to hand a piece of paper to every student, this is not a helpful number. It doesn't matter if I have 0.02 of a piece of paper because I can't give that to somebody. So in terms of significant figures, if I wanted to round this, it's like saying I have about 200, right? If I had to round it to a whole number, I have about 200. Now, if I had 201, that's still a whole number. But if I wanted to round this to my closest 100, still 200, okay? So the difference here is when you see a number like 200 in science, when you're talking about significant figures, it's assumed that this number is rounded, okay? Which is why these zeros are not significant. Obviously, this number is not rounded because the 1 is there. You measured that there are 201 things of whatever you're measuring. That 1 is a significant digit because it's assumed that that is an accurate measurement, okay? Same thing with the 0. Now this 0 is important because it's no longer an estimation. So significant figures can be a little confusing, and I'll try and make provide you some more resources like this video and add more clarification when we're in virtual Google Meets. But hopefully this gave you a brief introduction to significant figures and going over all of these units that we're going to be looking at this year. Again, these should help you with the practice problems that I posted on Google Classroom. But again, if you end up having any questions, you can always send me an email. All right. So make sure you guys hit that like and subscribe button, and I will see you in class. Peace.